remember, we already did chapter 5, so we're ready to jump up to chapter 6. So, again, book is a little bit off kilter of the way that I would like to teach it. I guess I need to write my own book. That's what I should do. I should just write my own book. Now I have all the lectures. I should just write it should be like a video book. Anyway, so I would do the first half of 6.1 and the first half of 6.3 together, and then do the second half and the second half together. So that's what we're doing. So what we're looking at in this first half of 6.1 and 6.3 is exponential functions. And exponential functions are different than polynomial functions, and they're different than rational functions. They're different than anything else that we've seen, because what we're going to do is we're going to take the exponent and we're going to take the variable and stick it up in the exponent. So the variable is no longer like on ground level, it's up in the exponent. And that means that we have to use very different techniques for solving this. So we kind of put the polynomial stuff aside and we're looking at something new. This is just an example, 2 to the x. The kind of formula, if you will, would be b to the x. And b is called your base. So we're going to talk about the base. I'm going to say what's the base of this polynomial. Okay, b to the x. And we're going to make 2 things about b. First off, we're going to let b always be greater than 0. So we're never going to have a negative b. Okay, we're not going to worry about that. And then we're also not going to use b equal to 1. Because if b equals 1, 1 to any power is just 1. That's too boring. So we're not using that guy. Okay, so always a number greater than 1. It could be a fraction, so we very easily could see something like, 1/3 to the x. Okay, definitely could see that. Okay. One other thing before we get into the graphing that I want you to be aware of is something that, again, you should have learned in algebra, but sometimes it's one of those things that you kind of forget. If I want to find, in this case, f of 0, and I put 1/3 into the 0 power, it really never matters what the base is, because anything to the 0 power equals 1. Okay, so we need to bring back that little tidbit. I got asked that in an interview question once about why does that equal 1, and I had to prove that, and let's just say I didn't get that job because most of the time I just take it for granted, but it's an important fact, and just trust me on that one, okay? All right, so before we do any solving of these guys, we're just gonna look at some graphs, because these graphs are different. We wanna get a good idea of them. And I say graphs because there are 2 graphs, and I'm gonna try to fit both of them, one here and one here. We'll see how that works. So we're going to graph f of x equals b to the x, and this first one we're going to look at where b is greater than 1. So b like 2 to the x, 3 to the x, 57 to the x. Okay. And I'm not going to make huge graphs so I can fit the other one down there. Now, some interesting facts about this graph is that we are going to have an asymptote. This graph has an asymptote at the x-axis, a horizontal asymptote. And the reason why, let's just assume we're using this, is there's absolutely nothing you could put in here to make it negative. If you put in a negative number, it just makes it a fraction. So if we were going to go 2 to the negative 1, that doesn't make it negative, it just makes it 1/2. So there's nothing we can put in here that is going to make us negative, so we'll have that horizontal asymptote. And then we're only going to worry about 2 points, and the 2 points we're going to worry about are, first, the point 0, 1. Okay. Every one of these guys is going to have a point 0, 1, because anytime you plug in 0, you get 1. And the other point that we're going to have is if we put in 1, that's going to give us b. So if we put in 1 there, b to the first power is just b. So every graph is going to have 0, 1, and then 1, and then whatever the base is. And this guy is going to look like, oops, I missed the pointer, like this. hug that asymptote here, so it's gonna get really, really small but never reach 0, but it grows indefinitely, and it grows, so it's actually called the growth function. The growth function. Now, what's gonna happen is as that B changes, this point is gonna change. It's gonna go up and down here, but it's always above 1. So it could be way up here, it could be way down there. So the steepness of the growth is going to change, but otherwise the shape of the graph always looks the same. So then let's look at the other one. If we're gonna graph f of x equals b to the x, but this time we're gonna look at b between 0 and 1. So as an example, this guy, 1/3 to the x. Okay, now that one is still gonna have a horizontal asymptote. Again, hard to see that horizontal asymptote because it's right on the line, so make sure you give me a good label on it so that I can see it. It's still gonna have the point 0, 1. And it's still gonna have the point 1b. But the thing is that b this time is in between 0, 1. So b is gonna be somewhere in here. So it's gonna have a point lower. And so what this guy looks like then when we draw it in is kind of the opposite of that one. So this guy is descending, or we call this decaying. So this is actually the decay function. So whenever you hear about that in math, this is what we're talking about. And it's gonna get closer and closer and closer to 0, but it's never actually gonna reach 0. There is only one exception to this rule, and that is extinction. So extinction of animals and plants, I guess, follows a decay function, and it gets closer and closer and closer to 0, but eventually with extinction, way out here, hopefully, way out there, or never at all, it will eventually hit 0. But that's the only, otherwise decay functions, they should not hit 0. They should get very small, but never, they don't actually ever hit 0. So, little tidbit there. So we got two graphs. We've got the growth and the decay, and then some things we want to do with them. So let's see if I have a better erasing the board situation here. We want to be able to use our transformations to move them around. So the first one I'm going to give you is y equals negative 4 to the x plus 2. Now, I told you that b was never going to be negative, and that it's not. B is 4. The negative is one of our transformations, isn't it? The negative goes boop and turns it over. So here we're going to have our base function. Okay, we have our asymptote sitting here. And we've got our base function, and since we're moving it around, I'm just going to put the point 0, 1. I'm going to leave the other point off for right now because we're just drawing a sketch here. Okay, it's a growth function because it's greater than 1, right? 4 is greater than 1. But what is that going to do to it? That is actually going to make every answer that was positive negative. It's going to go boop. So now we have a graph. It's going to have 0, negative 1. And it's going to look like this. But now, what are we going to do to that orange graph? The orange graph needs to be raised 2 units. But here's the dealio, guess what? That asymptote has to go 2 units as well. So there's our asymptote, 1, 2, asymptote. Give me a big old label so that I can see your asymptote. This point that was here goes 1, 2. It's actually back to where we started from. But are we drawing an increasing, or are we drawing this orange decreasing? So we're drawing a graph that looks like that. All right, so drawing transformations there. if you have to move the asymptote, you have to show me that you moved the asymptote. All right, now, again, if you've seen exponential functions before, what I'm going to talk about now probably isn't new to you, but let's just take a minute, and I'm going to blab to you for a minute here. When it comes to exponential functions, there's one exponential function that is most important, and it uses what we call the natural number. And the natural number is e, and e is a number like pi that goes on forever and ever. It's 2.718281, blah, 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 okay? So a lot of times we use it as 2.72, but we're gonna use our calculator to do this when we get to it. So we're just gonna use the E button on our calculator, but I'll show you that later. But you may have heard about E before. So E though, what we're looking at here, we almost always see E in the exponential function form. So f of x equals e to the x. Now, because E is greater than 1, this is a growth function. So x, y, horizontal asymptote, 0.01, and here is our growing function there. And we call this the natural growth function. Okay. So E, even though it pops up here in algebra or pre-calculus, in order to, the first time they calculated E was actually a calculus problem. So if you get deeper into calculus, not maybe calculus 1, but further on, you're gonna see the E to the X, and you're actually gonna see where it came from. But it didn't just, it's not like math people made it up. What happened was, as they were working through problems, they noticed that this function, this growth rate started to appear more and more, and it naturally happened. And so then they really started looking at it and applying it to the world. And what it is it's the natural growth rate. So if animals and plants were allowed to populate and reproduce naturally, meaning without human intervention, they would grow at this rate. So what happens then is, let's say that there is a bad couple of years, like there's a drought for a couple of years. And let's just talk about deer for the heck of it, because we have deer around here. The people at Fish and Wildlife, the scientists there, they might go out and they're studying the population of deer. And as they do that, they start to notice that over like the past 10 years, that the function is looking like this. And they say, oh, you know what? Deer are having a hard time with the drought. And the reason they know that is because here's where the growth function should be, and it has fallen below that. Okay? Another reason this could happen is because of development. So as we develop more and more into nature, the deer population has a hard time. First off, we build houses and roads into their fields and valleys where they feed. But also, as there's more development, there's more cars, and unfortunately, what do you see on the side of the road, okay? So deer are sometimes also affected by people. Again, Fish and Wildlife sketches that graph over maybe the last 20 years, okay, yearly, and they see this type of function, and they say, we've got a problem. And so they do whatever they can to naturally help the deer out. Now, people don't have that problem. If we were to graph the population of people over like the last 20 years, we're looking at a graph that looks like that. Our growth rate is so steep that we are truly overpopulating the world. We should grow here, not here. This is natural. The world can take care of us if we grow at this rate. If we go at this rate, the world takes care of us. And we know how the world takes care of us. I mean, the earth, the planet, by bringing in diseases like COVID, okay? By bringing in huge fires that are killing off animals, killing off food. The planet is saying to us that we have overpopulated, and so it's trying with all its might to bring our population down this way, bring the deer population back up this way. It's this balancing that's trying to get to that natural growth rate. But we got to let the planet do it, or we've got to help the planet out. So there's my little plug at climate change and overpopulation. But it's not like someone just said one day, hey, we got too many people on this planet. It's something that was graphed. It's graphed. You can visually look at it and go, holy crap, look what we've done. So these are, I mean, obviously mine is just a sketch, but if you looked up the growth function for world population, it's gonna unwind, it'll give you the actual graph, and you can see the steepness of it and see how incredibly high it is compared to what this guy looks like. So that's where the E really comes into play. And so we're gonna see word problems with it. And when you get into calculus, whether you're going to business calculus or regular calculus, either way, you are gonna see it all the time. It becomes very, very important in business calculus because of the growth of money. I mean, not that money grows, but how your savings account grows. But it has all sorts of applications to, again, growth, bacteria growth, looking at radioactive decay, temperatures cooling and heating up, all sorts of stuff. So you're going to see it over and over and over again. Okay. But anyway, we had to talk about that. So we talked about e to the x. And now we need to just solve a couple equations. So this first part, this 6.1, part, is somewhat quick. Of course, I say that, it's probably already been 20 minutes. That seems to be my norm. But let's just solve a couple equations, and then this one will be done. Okay, where it happened to my blue pen? So solving equations. So when we solve these exponential equations, what we're going to be looking at is something like this. I'm not going to do that one. That one's won't jump you off with a horrible one. How about we just look at 2 to the x equals, we'll start super easy, okay? We'll just start super easy. Now, I know that you can figure out what x needs to be to get to 4, but that's not the point. The point is how we're going to solve this. So I'm going to put a little 1 up here, and it's a good idea if you're solving an exponential equation, if there's somebody that doesn't have an exponent, stick a 1 on them. And in order to do this, what we need to do is we need to find the same base. And we're going to do that by rewriting the problem. And when we rewrite, we're going to go for the bigger number. We're going to leave this guy alone. So we're going to leave 2x. And we're going to ask ourselves, can we write 4 as a power of 2? And we can, can't we? So we can write 4 as 2 squared. Does everybody agree? Right? So all I've done is rewrite this guy using the same base as this one. So same base is your go-to. But here's the deal. If this 2 and this 2 are the same, don't the exponents have to be the same? So we can use that and say x equals 2. So like I said, we started super easy. Let's go with ones that's a little bit more challenging. Let's say, I'll put it right here just to use the board. Let's say we have 3 to the x plus 1 equals 81. Okay. Now, 3 is a nice small number, 81, much larger number, but we're going to need to know some exponents here. We're going to need to know some powers. So is 81 a power of 3? If we go 3 times 3, that's 9. Times 3 is 27. And 27 times 3 more is 81. So 81 can be rewritten as 3 to the 4th power. 81 is 3 to the 4th. So we make both of these 3. So now we can set the exponents equal to each other. So we can use the exponents. We can say x plus 1 equals 4. So x will equal 3. I didn't mean for this one to be 2 and this one to be 3. It just happened that way. Okay. All right, so let's look at a much uglier one. And they don't get super, super ugly here, but I'll make it uglier. Oh, what do I have written down here? Okay, it's not horrible. 2 to the 3x equals 16 to the 1 minus x. So the only thing that makes this one uglier is that now they both have an exponent that you're gonna have to work with. Okay, but 2 is a nice number, so remember we always wanna go to the smaller number. So we're gonna leave this guy alone, and we're gonna ask ourselves, is 16 a power of 2? Now it's 4 squared, so it's a power of 4, but it's also a power of 2, isn't it? 2 times 2 is 4, times 2 is 8, times 2 is 16. So this is 2 to the 4th. But who's still up there? 1 minus x. Don't forget this guy. So that means that we have 2 to the 3x equals 2, and we need to multiply through to the 4 minus 4x. Now we can get rid of the bases, okay? Ding, ding, they're the same. We say 3x equals 4 minus 4x. So now we just have a regular equation. We'll add 4x to both sides. So I have 7x equals 4, so x equals 4 sevenths. Now, looking back up here at this problem, was it at all obvious that the answer was 4 sevenths? Probably not. I mean, this one, yeah, okay, you could do that one. But once these things get uglier, the answers are like, I didn't know that's what the answer was gonna be. How the heck would I have known that, okay? So let's do one more. Again, a little couple steps uglier here. Okay, I don't have this one written down, so I just have to make it up here. So let me use my brain for a minute. Okay, let's say we have 9 to the 2x equals 27 to the x plus 3. Now, at first glance, you might say, that doesn't seem any uglier than the one we just did, but there's a problem with this one. 9 and 27, while they are related, can we write 27 as a power of 9? So is it 9 squared? Right, 9 squared is 81. So when we go for the same base here, these guys don't match up right off the bat. So what we need to do is we need to work on both sides. So we need to see, who do they have in common? So is this guy a power of 3? And is this guy a power of 3? So we're gonna go on both sides. So this one is 3 squared, not forgetting our 2x. And this one is 3 cubed, not forgetting our x plus 3. So we can't just use one side because they can't match up, but we can get them to match up if we go smaller. So we go down to 3 and we're good to go. So here we have 3 to the 4x equals 3 to the 3x plus 9. We can cancel out the bases and say 4x equals 3x plus 9. Subtract the 3x. And we have x equals 9. Okay. Same base, that is the key. Getting the same base. So then what happens if I give you this? Three to the x plus 1 equals 77. Now, all the other numbers that I put on the board have looked, they might be ugly like 81, but it's a perfect square, it's a perfect fourth. 27 is a perfect cube. All of these numbers have been nice, but is 77 a nice number? Can you write 77 as like 3 to a nice power? We cannot, can we? And so we're stuck. Okay. So when you go to do your homework, we're going to do those, but we're stuck here. So that's the next part of this section. But I like to do it this way, but we need to move on to the next section. Now, because I kind of fiddled with this, I'm going to change your homework on this one. So from 6.1, for right now, I only want you to do 58 through 63, and then 75 and 78. No, sorry, 75 and 76. And from 6.3, just 1 through 8. Okay, so since we split up the sections, the homework splits up with it. Okay, guys, so exponential functions, have at it.